We are both board members of the WIDE project, although neither of us did any of the work that is making this meeting possible. So we're going to just coast off of the WIDE laurels here, but don't thank us for the work. Thank the other WIDE members who did all of the work in making this possible. So we have what I hope will take us about 40 minutes or so to present to you all, and then we'll have plenty of time for discussions and questions. So you know, let's all enjoy our bento box lunch and the presentations. Shota, why don't you start first?
Hi, this is Shota Nagayama. Nice to meet you. So we will talk about the quantum internet and the basics of quantum computation and the quantum internet, and also the testbed effort in Japan. Okay, next slide, please.
Yeah, just have a next slide.
Hi, so very nice timing. So just RFC, the first RFC of the quantum internet has arrived. So thanks to the courses, how many courses are here? So, okay, Wojtek's here. So anyone is here? Maybe no, maybe online. So so the quantum technology is in developing now. So but the RFC is very good. So the architectural principles for quantum internet. So actually this RFC connects the quantum mechanics, quantum physicists, and also network specialists, and raising many problems we have to achieve in network engineering. So next slide, please. The goals of the quantum internet. Yes, of course, we should support distributed applications, of course, quantum, and future distributed applications, also heterogeneity and security, monitoring, so availability and resilience. So many things are similar to the internet today, so but quantum. Next slide, please. So the principles of a quantum internet, the purpose of the basic purpose of the quantum internet can be described with so entanglement is a fundamental service. So entanglement is a special state of qubits. So qubits is a basic the bits for the quantum computation, and so actually we can transfer quantum bit consuming this entanglement. So the entanglement is a fundamental service. And so I should say that, so this is a frequently asked question. So the quantum internet will not replace the internet today. So the quantum bit is different from so digital bits. As a particular, so the quantum data, quantum bit cannot be copied. So, but the the digital data can be copied, and so it's a very powerful. The copy is a very powerful functionality in the internet today. So we should use both of quantum internet and classical internet together. The next slide, please. So, so actually, so now there are two types of quantum networks. So quantum key distribution network and entanglement networks. So here we talk about the entanglement networks. So actually, the quantum key distribution is a quantum network application. So and so there can be so there is a special purpose network. So which is in the deployment stage, and the quantum internet is actually the entanglement networks which connects quantum computers and so other quantum devices with quantum data. And we will talk about that. So next slide, please. So maybe your turn.
All right, next slide. Yeah. So let me tell you a little bit about some of the general ideas behind quantum computing and quantum information. Really, quantum information, you can think of it as if you want to be sort of grandiose about it, you can think of it as our third information age. The first information age was analog information, recorded sound and things of that nature. And then the second information age is digital. Next slide, please. Next step, please. Yeah. So working with bits, of course. And then the third quantum age, or the third information age, will be quantum information. And so in quantum information, what we are dealing with is binary data, but the binary data has particular characteristics that we will need to understand and utilize effectively, namely superposition and entanglement. And each one of the binary data states has a complex probability amplitude that's associated with it. Next slide. So obviously all of you, everybody in this room knows that if you have n classical bits, you have n possible combinations for the state of your system. So in this case, we have 3 bits, you would have n possible states. In a quantum system, each of those states your system is not just in one of those states at a time, it is actually in a superposition of those states. So part of your probability amplitude exists for each of these 8 possible states here. And in this initial state here, you can see each of the 8 possible states from 0, 0, 0 through 1, 1, 1, they all have the same amplitude. But the distinction between the classical and the quantum system is that we have this superposition. The system is not just in one fixed state at an initial point in time. Next slide. So what happens during the course of a quantum computation is that the goal of this quantum computation is actually to gather that probability amplitude, that set of probability amplitudes, into the one state that represents a solution to your problem. So that's a really fundamental change to the way quantum system or algorithms are constructed. So algorithms are not just sort of iterated until you find the particular answer. What you have to do is you have to reconstruct the algorithm in a way that creates interference patterns, constructive interference and destructive interference, in the same way that if you're at the beach and you see waves of water at the beach, you'll see when you have 2 waves that are both at the peak and they come together, the peak comes together in what's called constructive interference. On the other hand, if you've got 1 wave trough and 1 wave peak, they cancel out and you're back to 0. That's destructive interference. You use these 2 phenomena together to create interference patterns in the process of solving a problem. And if you do this effectively, then the hope is that the total number of operations you're going to have to actually execute in the process of executing this quantum algorithm will be substantially smaller than the number you would have to do for an equivalent classical system. In particular, that doesn't mean, don't make the mistake of thinking that quantum computers will be some constant factor faster than classical computers. It's not that they're going to be 10 times or 1,000 times or 1,000,000 times faster. What's going to be different is the scaling of the algorithms in the quantum domain as opposed to the classical domain. Okay, next slide. So one way to think about the classes of problems that quantum computers we hope are going to be useful for is to think about problems that have a relatively small state description but a large state space. So for example, chess or Go, it only takes you a few bytes, maybe a few hundred bits to describe the current state of the game. But as we all know, the game tree expands exponentially as you go more steps through the course of the game. So chess and Go actually have a little bit too much structure to actually work well for quantum computers, or for quantum computers to provide you with a big advantage relative to classical computers. But it's the right sort of place to be thinking about this. And the kinds of problems that people are interested in solving with classical computers include chemistry problems, understanding the behavior of atoms and molecules. This was in fact what Richard Feynman proposed as the initial motivation for creating classical computers almost 40 years ago. Some classes of optimization problems are expected to be in the same category, and cryptography, probably most of you in the room have heard of what's called Shor's algorithm. A guy named Peter Shor in 1994 discovered that classical computers could use the generations of these interference patterns to find the period of a particular function, which then would allow you to factor large numbers, which in turn affects things like public key cryptography. And this this discovery happened at about at an important time in the evolution of the technology as well, where it was just starting to be possible to manipulate individual quanta in the laboratory, not yet to build systems, but to manipulate individual quanta. And so it generated all of this interest back in and excitement in the mid to late 90s. Right, next slide. And I think I'll hand it back to Shota at this point. If you haven't figured it out yet, he and I are tag teaming this on a section by section basis.
Okay, so about the quantum entanglement. So the qubit has a superposition, so we already talked about that. And also there's a special characteristic phenomenon of the quantum entanglement. So this connects multiple qubits to one quantum state. And so actually, by this entanglement, so we can use interference for computation. So in that example we showed, and so the answer was 110. So the probability was gathered to that, and so by entanglement, so that probability of 3 qubits is treated together. So if this qubit is 1, so the other is also 1. So if the other is 0, so the other is also 0. So this kind of characteristic, actually, this is a probabilistic. So because of the superposition. So, but the state of the Alice and Bob is connected or related. So, this is a quantum relationship. So quantum entanglement. So next slide, please. So actually, there are 2 aspects of the second quantum revolution. So the first quantum revolution was actually including semiconductors. So the IT technology today is also the product of the first quantum evolution, and the second one is the quantum computing and the quantum communication. So we utilize the quantum phenomena for the computation directory. And quantum computing, so it includes some kind of cryptography. So actually, and it's written the classical, so the cryptography today we use today. So often the newspaper says the RSAs will be decrypted by the quantum computing. Yeah, somehow yes. So but we need large scale quantum computers. So it will need more time actually. So, but the future, in the future, the quantum computing will be achieved. So we need some another technology. And yeah, of course, there's a post-quantum cryptography. So they are also under investigation. And so another answer is quantum communication. So we can deploy the quantum internet, and we can use quantum cryptography. So this cryptography can provide digital keys also. And so they cannot be decrypted actually. So we can detect eavesdropper if it exists. So it is very secure, but it's just theoretical. So we need engineering effort to achieve such a secure system. So so the quantum computing and the quantum communication, so actually the quantum internet is a kind of widely distributed quantum computing. So both are very important for quantum internet in the future. Okay, yeah, so there are 2 kinds of quantum networks. So yeah, I said, so there's an unentangled networks, so the QKD network, quantum key distribution networks. And so actually, the quantum repeating is a very difficult technology. So there was a kind of a spin-off deployment of the quantum networks. So at each link level, the quantum key distribution, this application is somehow terminated. So it's executed in each link level. So this is an integral network. And so the problem, one problem could be that we have to trust any router or intermediate nodes, repeating nodes in this unentangled network. So the quantum internet is an entangled network. So first we create the entanglement end to end. So from that entanglement, so we generate keys. Then, so we can achieve end to end secure key, and also so distributed. So it can transfer a quantum bit end to end. So this will achieve the quantum computers communication and other applications like the high precision sensor networks. So there are journal papers which is talking about the ultra high precision telescope, and so and other many other applications like the Byzantine agreement problem. So next slide, please. So actually, there is a very big gap between those two technologies. So because the entanglement networks is actually the quantum computer network. So the quantum computer itself is a very difficult problem. So it's very difficult so research achievement. So and we have to connect such quantum computers. So the quantum internet will be more difficult. But yeah, we will do that.
So actually, written there in the middle, it says there's a series of steps from defined in a paper by Vainer, Elkus, and Hansen. David Elkus is the middle author in that, and he's sitting up here in the front. David, wave hi. So if you want to talk to one of the authors of this, catch him afterwards.
Yes, three big applications field of the quantum internet. So one thing is this. So the distributed cryptographic functions and distributed computation and the sensors. So yeah, so I talked about the just the secure communication, but quantum computing, distributed quantum computing will provide other cryptographic applications like the blind computation, the secure computation. So today, of course, we process many applications on the servers and the cloud, and but actually the administrators can eavesdrop what the process is doing or the data. But in quantum, so everything can be blinded. So I mean, the administrators so technically cannot see the data and even what the program is doing. And as applications, so the distributed computation. So the quantum computer has a special power. So so more qubits will result in the more computational power. So that example which shows that the 3 qubit has of course 8 states. So more qubits, so we will have the more candidate of answers, and we can retrieve the answer from that. So the rapidly increasing the state space. So that we want to connect more quantum computers, and we want to achieve the so speed up, quantum speed up with more qubits. And the third one is the quantum sensors. So by quantum internet, so like IoT today, so the more sensors can be connected over the quantum internet. So the telescope. So I talk about the telescope and also the distributed clocks. So we can achieve the very high precision synchronized clocks, and also as a reference frame can be precisely synchronized. So this is also quantum power. And so on the journal paper, so the telescope is just is a good application and a good example. And I think so we can target not only the space but also the any other we can target any other things like the under Earth or so human itself. So this also can be so this is like the IoT today. So but with quantum we can do some more precise high precision sensoring. So reduce dependency on public one. Yes, so the distributed computation. So in computation, so we have the computational complexity. So in distributed computation, so there is a communication complexity, and distributed quantum computation can reduce the communication complexity in such distributed programs. Okay, so what do we want to achieve? So the quantum data center and quantum wide area networking. So actually to achieve a large scale quantum computer, so I'm talking about just quantum computation. So the distributed quantum computer should be required. So the many number of quantum computers should be connected and should be clustered. So like the supercomputer today. So from that, so of course we can.
You're drifting away from the mic. Be closer to the mic.
Sorry about that. So from that, so of course we can expand that network to quantum internet, and we can connect such data centers. And in the future, so the general users will be possible to send some kind of quantum data from their local personal quantum computers to the quantum data center, and we can execute a quantum computation on the quantum cloud, and we can achieve more large quantum computation by connecting more quantum computers over quantum internet. So of course we can connect the quantum sensor network, and we can collect quantum data from such quantum sensor network and processing such quantum data in the quantum computer. So where are we? It takes time. Oh. Okay, so actually there are many world efforts and many efforts in the world. So about the testbed, so stick to testbed, and so actually Quantum Internet Alliance, the project has raised in 2019. So around that, and they are also has a big budget and working on the quantum internet, so basics, so including the physical things and also the computer network engineering, and so they are also doing the distributed quantum computation too. So and from 2020, so suddenly the United States announced that they will invest a big budget to the quantum networking. So this great part is quantum networking. So it includes both of the quantum internet also and also quantum interconnects for large scale quantum computer. So in the 2010s, it's like the quantum computer, the engineering, so actually building quantum computer has been started, and so around 2020, the quantum networking is also in such phase. So in Japan, QITF and also the wide project collaborates, and we are working on the testbed efforts. So actually now there are so many testbed projects over the world. So I think this is very nice. So they may use these different physical technologies, but so if there are many type networks, so then we can connect that, and then we will achieve the first quantum internet. So that will be the beginning of the quantum internet. Next slide, please. So actually the quantum signal repeating was very difficult. So the carrier of the quantum bit between the nodes is the photon, and the photon can be so absorbed in the fiber. So exponentially the numbers of the photon arrives to the next node decreases. So, and we cannot amplify. So because photon is not arrived, photon does not arrive. So we need another quantum repeating technology. So other than the amplification. So, but the quantum physicists made efforts, and finally, these days, the proof of concept of quantum repeating has been started to be demonstrated. So now, from now on, so I think we think so the third step and the fourth step are very important. So to achieve the system, actual quantum networking system. So the overall quantum networking system, like including routing and also multiplexing, so everything is very important. So the star topology should be the smallest, the beginning of such system demonstration. And if we achieve such system with scalability and robustness, so we can expand such network to the more complex and large-scale networks in the fifth stage. So actually, so yeah, this is kind of just saying. Because of the difficulty of the quantum signal repeating, so there was another candidate of quantum networks, so the trusted node QITF network. So those two are so different direction. So our way is the right one.
All right. My turn. So that gives you a little bit of an idea of sort of where things are worldwide. But let's talk about, rewind a little bit and talk a little bit more about what has to happen at sort of the technical level in order to make all of these things happen. So what we're going to build is a quantum repeater network. And like Shota just said, you know, the word repeater, it doesn't mean the same thing in the quantum world that it means in the classical world. It's not just an amplifier because you're not allowed to do that. Right, so next slide, please. So the job of a quantum repeater network is to make end-to-end entanglement between a pair of nodes, modulo some arguments about whether or not, you know, sort of relative timing sorts of things. Next slide. And because this quantum entanglement is a consumable resource, the job of the network is to make lots and lots of it, to keep repeating, because you're using it as a resource while you're actually executing distributed computations. Next slide, please. So one of the things I really want to emphasize here is that making this end-to-end entanglement is a distributed computation. So quantum repeater networks are not going to be just like classical packet forwarding where you fire a packet and forget it and you don't have to worry about sort of operations along the path. You just sort of assume that the packet forwarding will happen. All of the nodes along the path are going to have to be involved in the creation of this end-to-end entanglement. And so this suggests that it will be a circuit-oriented model with stateful operation at each of the nodes. And so that's the kind of area where people in this room can really contribute, is working out some of the operations that are involved in this. Next slide, please. So if that's the job of a quantum repeater network, then the job of an individual quantum repeater is, next, first, to make base level entanglement over a link. So you've got a fiber and you've got a couple of what are called quantum repeaters that are at the ends of this fiber, and their job is to make entanglement that covers one hop. Okay, next. The second thing you got to do is, once you have a set of these one hop entanglements along this path, you have to couple them together to create this end-to-end entanglement that's going to be used by the applications at the end nodes. Next. But the problem with this is that these systems are very, very noisy. And so what you have to do, in addition to just creating this entanglement, you have to monitor and manage the errors in this. Now, QEC is quantum error correction, and in some cases it builds on classical error correction techniques. In other cases, it's completely unique to quantum stuff. Purification is a form of error detection that will be deployed in the early systems, including the early quantum internet. And in that case, what you're doing is you're building generic entangled states, and when you detect an error, you just discard and restart, and that's fine because you're not sacrificing any of your critical application level data. Next. And then finally, again, this is the role for the people in this room. The fourth thing you got to do is you have to participate in the management of the network, including routing, multiplexing, security, naming, all of those sorts of things that, trust me, do we have any physicists in the room? I hope not. We're all computing people here, right? The physicists don't understand this stuff, right? Trust me, they don't understand this stuff. Next slide, please. So if that's the job of the quantum network and of a quantum repeater node, then the job of a quantum internet, this will look familiar to everybody in the room. Next slide. We need to do all of this next across heterogeneous physical networks and heterogeneous logical, networks that are heterogeneous both physically and logically, and in an environment with minimal trust between the networks, including potentially the presence of malicious nodes and knowing little or nothing about the internals of those autonomous networks that collectively make up the quantum internet. Okay. All right, next. So, my group at Keio has been working on this stuff since 2007, give or take. Excuse me. And we have planted a number of flags on every networking related problem we can think of. And every single one of these is just a first step. There's still a long ways to go with each of these. So we have proposed a network architecture that builds on Joe Touch's recursive network architecture, which we call the quantum recursive network architecture. So Joe was a co-author on this 2013 paper in which we proposed the quantum recursive network architecture. We have worked on layering in protocols and how you're going to actually structure the communication stuff of this. This appeared in a Transactions on Networking paper back in 2009, but what's in that particular paper is already substantially outdated. So you can read it for historical purposes, and there are a couple of other sort of technical things that are valuable in it, but we're taking a very different approach nowadays to the actual classical communication. Routing, picking the best path through a network is one of the things we worked on. When Shota was an undergrad 15 years ago, there was another undergrad along with him, and this was actually the bachelor's thesis of my other student, Sato, at that time. Next. And then multiplexing, dealing with how you're going to share resources in a network where you have multiple connections that are competing for access to the network. And this was work that was done in conjunction with a student of Hiroshi Esaki. Esaki-san's the WIDE project director. So it was a collaboration between our institutions on that. Next. And next. So we also worked on internetworking. I mentioned earlier that you might have heterogeneous networks that are physically and logically heterogeneous. Part of Shota's PhD thesis back in 2016, was it? Was working on how you can deal with that interoperability when you're dealing with networks that have separate methods for managing the errors, separate error correcting codes in it. Next. More recently, we have done work on what happens in operation of the network and dealing with the network operational security. Now, we all have sort of an idea of what happens when something goes wrong with, with BGP or the classical routing system. You get routing black holes and things like that, and those are problems, right? But one of the questions we've been asking ourselves is, when we build this quantum network, will there be additional vulnerabilities? Will there be differences in the way in which network operations happen that will result in making it harder to actually manage quantum networks than it is classical networks? And we found that, in fact, it's possible to sort of fake some of the operations on the network in a way that would result in the network winding up partitioned. And so we want to avoid that. And so we proposed a relatively simple mechanism that helps prevent the network from being partitioned when somebody hijacks a single node or a single node misbehaves. Next. We also have worked on applications of these quantum networks. A label there got missed, it got lost, but that's quantum Byzantine agreement. So how you would do Byzantine agreement in a secure fashion across the quantum internet. And one more. Next. Also, we have worked on the quantum equivalent of network coding, for those of you who are familiar with network coding. All right, next slide. A lot of our work has been just paper-based design, but we are now on our 4th generation of quantum networking simulator. And this is our large-scale simulator. If you are familiar with the classical network simulator OMNet++, you looked at this and you immediately saw that this is an OMNet++ GUI. So we have been building on top of that there. And if you are interested in this, the QR code in the upper right there will take you to the repository. This is all open source code released under a FreeBSD 3-clause license. That will take you to the GitHub repository. And the link in the lower left there will take you to a Google Collaboratory notebook that actually runs this in a Jupyter notebook. In that case, the Jupyter notebook itself is running on the Google server, but in fact, what it does is it actually downloads a WASM copy of the simulator and runs the simulator directly in your browser. So it will run it locally. Okay, next slide. One of the things we have been doing, there was some discussion at the QIRG meeting on Monday about, well, maybe we need more more consistent terminology, and that's definitely true. There's disagreements about even what the word switch means. For some people use the word switch to mean a node that actually includes quantum memory. We use it to mean only a device that's routing photons from one place to another. But one of the things we have proposed in some of the work we've been doing is a set of network icons, and these are actually available for use in the draw.io package or diagrams.net if you've been using that. All right, next slide. And let's see. There we go. Some of these things are described in a paper we published at IEEE Quantum Week last year, and that URL will take you to an available copy of that. And I think that hands it back to Shota.
Okay, yeah, thank you, Rod. So I will talk about the quantum internet testbed effort in Japan. Oh, this slide. Okay, so let me introduce briefly about the quantum internet task force. So 5 years ago, so there was many quantum computer projects, but there was no quantum internet projects actually. And so I thought, my idea was the quantum version of the wide project. So the researchers should get gathered and we should collaborate and to achieve the actual quantum internet. So the quantum internet requires many measures, right? The quantum physics, quantum optics, the computer networking, computer systems. So always, of course, we need always specialists. So everyone. And so we talked to, I talked to every quantum internet researchers at that time, and we organized this quantum internet task force, and I'm doing the founder and representative of this one. Next slide, please. So, and of course, we have the senior researchers too, so they are basically the advisors, and our strategy is like so yeah, I love the internet strategy. So I think we think this is important to do both of the real testbed and also simulation. So we are doing I want to do the trials and errors. So we do the actual implementation in real testbed. But yeah, of course, it should be start from a small network, and also we should research so validate that implementations, so if it can be scalable or if it can be robust. So alternating those two aspects, so real testbed and simulating, is very important. And next slide, please. And yeah, so this is what we are making. Making the blue part is actually the quantum hardware, the quantum memories and the quantum optical devices and the quantum control devices. And so this is a kind of the quantum physicists, especially experimentalists as a field. And also so with just those blue devices, components, so this is just emitting the quantum signal, just receiving the quantum signal. So receiving, not receiving, actually the detecting the quantum signal. So we have to make such kind of a quantum signal, so emitting and detecting to the more system. So the red part is a kind of the networking system software and the network system hardware. And so this is our overall system of our target. So of course we need a synchronization system, and also we need computers. So like some of you may know that the quantum application today. So like the interface is actually on the laptop on the computer today, and it can access to the quantum computer. So yeah, this is something like that. So this is similar. So we can execute. So actually we can trigger the quantum distributed applications from the computers today, and we can derive the quantum devices, and the quantum communications will be derived, and quantum distributed applications as well. So next slide, please. So yeah, so in QITF, so I have many collaborators, so also including the experimentalists and physicists, and so I have collaborators in wider project too. So we have many measures, and putting those things together in this testbed, and we are building at first a lab area network. So we just started a laboratory in Tokyo area. So Shinkawasaki, it's close next to the Yokohama, and yes, so from laboratory network, so we will expand that to the data center size network, so the over 200 meters. So after that, so we will expand this network to the other campuses. So this will be the beginning of the quantum internet in Japan. Next slide, please.
All right.
So you all now know everything you need to know about the quantum internet, and you're ready to dig in and write code, right? Everybody's good for that. All right. Well, maybe not. One of the other efforts we are involved in here in Japan is we're actually involved in the creation of an undergraduate curriculum and set of courses that are actually to be used by a set of universities across Japan to create an undergrad degree in quantum engineering. Within all of that, that's headed by Keio University, she's now down in Okinawa. But within that group, my responsibility is actually for quantum communications. And so the first course we've created for that was called Overview of Quantum Communications. Of course, the focus is primarily on dealing with things here in Japan, but it was easy for us to do it both in English and in Japanese. So this is Mikhail Hajduszek, who's a project assistant professor in my group. He did the English and I did the Japanese versions of these things. And we are making all of these materials available, Creative Commons, and all of the videos for this are actually uploaded on YouTube. So this is a total of about 12 hours or so worth of material. So about the time it would take you to read, one popular science book on the topic, give or take. Next slide, please. You can get a draft. We are taking these materials and we are turning them into a book. And that book will also be available, Creative Commons, CC by SA. It is on GitHub. That QR code there will take you directly to a recently compiled copy of it. The book is not yet complete. There's still things that are going on. You'll see as you're reading it that it still needs quite a bit of polish, but we wanted to make it available to you all here this week. And it's a companion to the course. And next slide, please. If you contribute to the book, we will add your name to the contributors page, by the way. So the contents, it's about 300 pages long right now. There's still some stuff that needs to go into it. It should follow on from a basic introductory understanding of quantum computing, but you don't have to be very deep into it in order to work with this. And if you really want to try it without even any other quantum background, there's enough basic material in it that I think you'll be able to get through. And the only math background you need for this is vectors and some basic linear algebra and discrete probability and complex numbers, and you're good. Next slide. So that's the kinds of things that are included in this. And next slide, please. And yes, if you download this, we would love to have your feedback. You can contribute that feedback either through a Google form that is linked here or via GitHub issues and pull requests. And we've already had one this week on it. And I was just promised in the hallway before this started a second set of comments on it. So we look forward to your contributions to making this book as good as possible. And let's see, next slide. I think that's it. Oh, and then of course, finally, the Quantum Internet Research Group, my co-chair Wojtek, I saw him here in the room somewhere. Wojtek, where'd you go? There he is. Wojtek and I are the co-chairs of the Quantum Internet Research Group, which met on Monday. This is very old data. I think there are about 500 people on the list right now. But we look forward to your participation in that as well. Next slide, please. And that brings us to the open mic portion of this. Questions, comments? Help me, I don't understand this, right? The mics are open on the, let's see. Wojtek.
Hi, Wojciech Kozlowski. I just have a comment to make about when Shota said that quantum internet will be more difficult to build than quantum computers, and I just like to qualify that's true for the case of building fault-tolerant quantum networks where you're actually connecting quantum computers. But because the key resource of the quantum internet is entanglement, which is achievable between already 2 qubits, one can actually already construct applications on a much smaller scale. And so it's also important to notice that there's a lot of functionality in between today and the long-term fault-tolerant quantum networks. So yes, full quantum internet will be harder, but there's a lot of space to actually get some use out of it before then. Thanks.
Yeah, good. Thanks. That was a good comment. We are not hosts or chairs of this session on this, so I can't see who's actually in the queue elsewhere. Dean's name pops up here at the top. Are you Dean?
Yeah.
Great. You're up.
Dan Bogdanovich. So I'm an amateur. I like to read about this and find out. But here, what I'm struggling with is you have a quantum computer, and there's a certain quantum state inside that. And if you want to transfer that state, you have to measure it. At the moment that you measure it, it collapses into a single state. Now, how can and in networks, we were using, here's the data, we were serialize it and send it across to another computer in order to do some additional processing. So, okay, you can create entangled qubits across distance, and they will do some calculation, but how can you then so with a third-party system, so that means if you want to create a larger computer, i.e. through a larger network, you always have to sort of start from zero every single time when you're building up the whole, if you want to say like a network, you have a network for a period of time and then it doesn't work and then you have to rebuild it again.
Yeah, there's a whole lot going on in what you're saying, and a lot of that's pointed in the right direction. And there's one particular magic word we haven't said yet: teleportation.
I was afraid about that because this is where I'm completely getting lost.
So I said earlier in one of the segments where I was talking that entanglement is a consumable resource, right, inside of the system. And so the job of the network is to make this end-to-end entanglement. And the entanglement is actually used for several different things, but one of them is to transfer data from here to there, and in the process, you consume that entanglement, and it goes away, and your original data also goes away over here, but over here your data gets reconstructed, and that's quantum teleportation.
Okay, so the function of the network is to create entanglement between qubits over geographical distances.
Yes.
Okay.
And one of the things we use that for is sending data from place to place. There are other things we use it for, but that's one of them. And so you'll sometimes read papers, particularly written by, I've already insulted the physicists once, I might as well keep insulting them. You'll read papers written by physicists that say teleportation is an application of the quantum internet. That's kind of like saying TCP is an application of IP, right? It's it gets you partway there, but the question is, what are you going to do with it, and why are you doing it? Right? It's not, sending data from one place to another is not an application in and of itself. Let's see. Next in the queue. Shota, anything to say on that for the? Dean's name hasn't gone away, but I'm sorry, I don't know your name, so you're up next.
Joey Salazar. So you mentioned QUIRC before, and in the spirit of keeping contributions going, I was just wondering if there is like a relationship between QUIRC, the work you're doing here, and the new, what was it? I keep forgetting the name. The one that is meeting tomorrow, the PQIP, post-quantum using protocols, or if there's no relation at all. Somebody's shaking.
There is not yet any relationship between the new, let's see, is that a working group or a research group that's meeting tomorrow? I forget.
Working group, I believe.
It's a working group. So yes, they are talking about post-quantum cryptography. And so that's classical cryptography designed to work in a world in which quantum computers exist and can challenge RSA and potentially Diffie-Hellman and things like that. So that's what they are after. The work that they're doing is very independent of the work that we're doing in QIRG, but the knowledge that you build in both, I think will be beneficial for both of those.
All right.
Wojtek, do you have any other comments on the relationship between QIRG and the new post-quantum group?
Yeah, I had a look at their meeting. They're explicitly excluding any talk about quantum internet and QKD. So no.
Okay, so no overlap in terms of technical material. So we have a good clean separation in that. But I think you'll find valuable shared learning in those environments.
Absolutely. And then just one more question. I had previously read the RFC, well, the now RFC, then draft for the quantum architecture principles. Mm-hmm. And then you also mentioned the paper that you published more recently, I believe, the quantum internet architecture, I think. So I was just wondering if those are the same or like how different they are. Like if I read the RFC, like would it still be a good idea to read this other one, or if they're pretty much the same?
The architectural principles draft explains some of the same kinds of things that, or now RFC, sorry, explains some of the same things that we've talked about so far in this session in terms of what entanglement is and this idea of entanglement as a service. I think Wojtek might have been the one who came up with that phrase, entanglement as a service. In my brain, it's associated with him. But so it explains some of those principles, but it doesn't lay down any specific design decisions. And that paper that I put up there with our quantum internet architecture, those are the recommendations of my group for these are some of the key architectural decisions. Whereas the RFC talks about talks about the architectural principles. So I think in that sense they're very complementary. You should probably read the RFC first and then the paper second. Other questions? Do we have anybody online? Actually, there was some comment. What was there was a comment.
Alexander?
Are you Alexander?
Yes, that's me.
Okay, good.
I'd like to just clarify one aspect. In a set of previous slides, there was a statement that an optical fiber can absorb a photon, and therefore there will be some signal loss. But then in another context, you were saying that there is quantum communication that works with satellites.
Yes.
That is, there is no fiber in there.
Yes.
So how to reconcile these things? Why don't we just use the flavor that doesn't use fiber so we don't have the problem?
getting individual photons down from low Earth orbit or medium Earth orbit or geosynchronous orbit is an astounding technical accomplishment. Various countries, Singapore, Canada, Japan, have been working on satellite quantum communications, and then China launched a satellite and just leapfrogged the work from everybody and demonstrated the creation of entangled photons on the satellite and their distribution to two sites on the ground. And yet still, the success probability of getting those individual photons down is very, very low. It's 10 to the minus 7 or 10 to the minus 8 or something. And yet they're doing, the fact that this works at all is just incredible. There are a couple of disadvantages to the satellite-based approach. One is that your ground station for this needs to be a telescope that's about this big around. It costs about $750,000, right? And your satellite costs about $600 million, right? And then the other big disadvantage is that because the satellite's in low Earth orbit, it's only overhead for 6 minutes a day, right? So you can create entanglement for 6 minutes a day using this one particular satellite. So they're complementary approaches. Which one's going to be the better way to create entanglement across an ocean? Well, you know, these quantum repeaters we've been talking about, you know, Shota's slide earlier showed a laboratory with an optical table that's just starting to get built out. You know, they're optical table sized things. We are a very long ways away from anything that could possibly be put into a fiber, an undersea cable that can be deployed between here and the United States. And so we think there are likely going to be roles for both. Although I'm a collaborator on some research actually in which we proposed the distribution of quantum entanglement via cargo ship, which is yet another way of potentially distributing it.
Thank you.
Yes, actually, yeah, free space communication has a specific problem, so like the diffractions of atmosphere. So we have to shoot the photons to the receiver in quantum communication, but such photons often cannot arrive to the receiver in the satellite communication as well. So.
Yeah.
Anyway, we have problem.
for quite a while, and I think it may still actually be true. Well, no, obviously the satellite superseded it, but for quite a while, the longest distance distribution of entanglement was between two of the Canary Islands, which was between telescopes on two peaks in the Canary Islands, 150 kilometers or so, and that experiment was done by a group from Vienna. By Anton Zeilinger's group, and Zeilinger was one of 3 recipients of the Nobel Prize last year for his work on demonstrating the existence of entanglement experimentally, including that work.
All right. And then I have another high-level question.
Sure.
Do we have anything in the roadmap that would accommodate this use case? So imagine New Horizons flew to Pluto. It took a few pictures in this much time, and then it took this much time to send it all back here. Do we have some tool on the roadmap which would allow us to send it back here like this?
Oh, no, you know, so we actually don't have a slide in that on this presentation, but that's one of the key things we really have to iterate or repeat when we're talking about quantum stuff. This entanglement over a distance, weird things happen to the states sort of simultaneously, give or take, but you can't use it for transmission of data faster than light. Don't make that mistake, right? And creating this entanglement is way harder than just pumping a bunch of light from a laser down a fiber. And so the entanglement will enable very different applications and will be used in a very different way than just transfer of large amounts of data. So it's going to be very different in that sense. Right, people are starting to move out, and it is now 12:45. I'm not sure what's next in this room, but I know other people have various meetings to go to, some of which might start at 1. So the slides should already be up in Data Tracker. We had a little bit of a glitch with MeetEcho and Data Tracker right before we started, but the AMS, the Secretariat staff, should have already uploaded them for us. So thank you all for being here, and those of you who are, thank you for the bentos. Clean your bentos up and please discard them. And for those of you who are signed up for tomorrow's tour of the lab, We have about 40 people going on a tour tomorrow of a lab at Yokohama National University. That will leave from the front door of this building at 2 o'clock. So see you then.
Thank you so much.